So welcome everyone to the second session of the conference on topological aspects of strong correlations and gauge theories. The first speaker this evening will be Professor Dima Kharzeev. Professor Dima Kharzeev is a distinguished professor and director of the Center for Nuclear Theory at Stony Brook University. His research interests include quantum field theory, nuclear physics, condensed matter physics, and quantum information. And he is well known for his work on chiral magnetic effect and chiral matter, which will be the subject of his talk today. As we had in the morning session, I would request people that depending on whether the speaker wants it or not, you can ask questions in between or at the end of about 45 or 50 minutes. Professor Kharzeev, you can go ahead.
Thank you very much. It's a great pleasure for me to be here with you, if only virtually. So I'm very grateful to the organizers for giving me this opportunity. So I was instructed by the organizers to start from the very beginning and be pedagogical. Keep in mind students who attend this wonderful meeting. And so this is exactly what I will try to do. And in the spirit of being pedagogical, please do not hesitate to ask me any questions the very moment this question arises in your head. Don't wait till the end of lecture. So just please go ahead and ask any questions that you may have. Okay, so I'm going to talk about all aspects of the physics of chiral matter. I will start from chirality in classical physics, and we will actually see that there are many similarities between the physics of chirality in quantum physics and the physics of chirality in fluid dynamics in the Stokes regime of low Reynolds number. And there is even an analog of chiral anomaly in this theory. Then we will talk about chirality in quantum theory, chirality in gauge theories, discuss the so-called chiral magnetic effect, and other examples of quantum transport induced by quantum anomalies. Then I will talk about ongoing search for chiral magnetic effect in heavy ion collisions. Just last week, there was a very exciting announcement of the result from isobar run at relativistic heavy ion collider. I will discuss it extensively. We will see that in fact the isobar run results support the existence of CME, probably at about 2-3 sigma confidence level, once you correct for the measured change in multiplicity between colliding isobars. Then I will talk about chirality and quantum computers. And here I will talk about two different things. So one direction would be the use of quantum computers to study real-time chiral dynamics. And this will be the work based on my collaboration with my friends Yuta Kikuchi and Kazuki Ikeda. And the second direction will be to use chiral materials to maybe think about new architectures for quantum processors. Okay, so now in the spirit of starting from the very beginning, let me start with the definition of the word chirality, which comes from the Greek word for hand. And I like this classic definition given by Lord Kelvin in 19th century, who said, I call any geometrical figure chiral if its image in a plane mirror cannot be brought to coincide with itself. And of course, hand is a classic example of a chiral object. And this is why it gave the name to this concept. So chirality, of course, is encoded in our DNA. The double helix is a chiral structure. If you actually look at DNA molecules, then they are quite long, and they typically form complicated knots. And most of the complicated knots are chiral. And it is a very active subject in mathematics, classifying the chiral invariance of knots. So for example, if I ask you whether this knot is chiral or not, the answer is not trivial. And so people devised and continue devising more and more sophisticated invariants, which allow you to tell whether a knot is chiral or not. But this is still an open problem, because even the most sophisticated invariants are not able to detect with 100% certainty chirality of complicated knots. So this particular knot is chiral, and you can use one of your favorite knot invariants to check this. So we are also chiral objects. So living organisms contain almost only left-handed amino acids and right-handed sugars. So for example, if you are given a left-handed sugar, you would still be able to taste the sweet taste of sugar, but your body would not be able to metabolize it. And this is the basis for some artificial sweeteners. Most of the drugs on the market now are chiral, even such mundane and common drugs like ibuprofen or penicillin. And if you look at the roadmap for pharmaceutical industry, you will see that one of the main goals of the industry is obtaining chirally pure drugs. So for example, you want to obtain a drug only in left-handed form or right-handed form, and not an achiral mixture. So why do you want chirally pure drugs? Well, there is a famous example of thalidomide that is explained well in this famous TV series by Walter White. So you can look at episode 2 of the first season to hear this. And the story goes as follows. So people developed this thalidomide drug in its naturally derived form, which is left-handed. So it passed through all clinical tests. And then they started to synthesize it. And when you synthesize it, you get an equal mixture of left-handed and right-handed molecule. And with time, it appeared that the right-handed version of the same molecule is a powerful poison. And it gives you a huge death rate among newborns. And so this pharmacologist, Francis Kelsey, figured it out and blocked the sale of this drug in the United States and eventually throughout the world. So it appears that our sense of smell is chiral. So for example, if this were in-person lecture, I actually do have, with me, both left-handed and right-handed form of this limonene molecule. So left limonene is easy to get. It's used, in baking cookies and so on, and it's a nice, pleasant smelling substance. The right one is quite hard to get, and I had to ask my friend, who is a chemist, to get the right-handed form of it. And once you smell it, you immediately realize why, it's not such a popular substance. It smells, really horrible. And the surprising fact is that it's really the same molecule, but because our sense of smell is chiral, our body clearly tells the difference between left and right. And when I let people smell, this two different chiral forms, it's really impossible to mix up the left and the right. The difference in smell is really striking. So now the question is, I told you that we are made of either left or right-handed molecules exclusively. And so the problem is, why is life chirally asymmetric? So this is one of the big problems of nature. And long time ago, Abdus Salam and collaborators proposed that the origin of left-right asymmetry of life could be a violation of parity in weak interactions. So the point is that in weak interactions, of course, you only couple to left-handed fermions. And if you consider a molecule, then, of course, the molecule is bound by Coulomb interaction, but in electroweak theory, there is an admixture of neutral current exchange, which breaks parity. And therefore, if you compute binding energies of left-handed molecules and right-handed molecules, you get a difference in binding energy. And so Salam proposed that this could be the origin of left-right asymmetry of life. Now, unfortunately, it appears that since the contribution of neutral current to binding energy is really tiny, the asymmetry between this left and right molecules, even after so-called chemical amplification in the synthesis, is still very small. And even though there were some claims that this would be enough, the consensus at present is that the difference in binding energy is not enough to explain asymmetry between left and right. So you may say maybe it just happened by chance on Earth, and maybe somewhere in space, the sugars are right-handed and amino acids are left-handed. But all examination of meteorites that we could get hold of tell us that chirality of organic molecules is the same everywhere in space. And so there really has to be some fundamental symmetry. So the most popular, or one of the most popular hypotheses at the moment is that it actually is the violation of parity in weak interactions that creates chirality of life. But it's not the difference of the binding energy, but the fact that beta decays emit left-handed electrons, because of course they are mediated by weak interactions. And people have measured in experiment the cross-section of molecular breakup for left-handed and right-handed molecules by left electrons. And the asymmetry in breakup cross-sections is actually quite sizable. It's a few percent. And so one of the plausible ideas, which is known as Wester-Ulbricht hypothesis, is that the asymmetry of life on Earth is induced by weak interactions through the beta decays. Another explanation which could also work is people studied to shine circularly polarized light during the chemical synthesis, and this also produced sizable asymmetries between left and right. But if you accept this hypothesis, then you have to come up with an explanation why the radiation, light, or cosmic microwave background would come in a circularly polarized form, and this is not known at present. Okay, so now the main contents of my lectures will be the use of chirality for transport. And one of the first uses of chirality for transport was proposed by Archimedes. So this is the famous Archimedes screw. So he proposed it to pump water out of hulls of big ships. And if we now look at Archimedes' screw from the point of view of discrete fundamental symmetries, then we see that when we rotate the screw around its axis with some angular velocity omega, the fluid gets transported along this axis, which is parallel or anti-parallel to angular velocity. And so we generate a vector out of a pseudo-vector. So, of course, this can be possible only if parity is broken, because vector is odd under parity, pseudo vector is even under parity. And so this phenomenon requires breaking of parity. And of course, the screw itself can come either in left-handed or right-handed form. And so a particular Archimedes screw definitely breaks parity. And this is how this transport happens. So now to make analogy with quantum phenomena that I'm going to discuss more close, it will be interesting for us to consider tiny chiral molecules with small size, which are characterized by low Reynolds number. And in this case, of course, there are many chiral molecules that we know, but to make them move in the fluid, we have to find a way to rotate them. And how do you rotate a tiny molecule? Well, the idea was proposed quite some time ago by Baranova and Zeldovich. So Zeldovich is a famous name, but Zeldovich on this paper is the son of famous Yakov Borisovich Zeldovich, who worked in Florida in his late years and passed away last year. So the idea of Baranova and Zeldovich was to rotate molecules by using the coupling of an external electric field to the electric dipole moment of the molecule. So the molecule has electric dipole moment, and then if you rotate electric field, the molecule starts to rotate, and because it has chirality, it starts to move in a direction which is determined by chirality of molecule. And of course, the same can be done with the magnetic field as well. So this is not an animation. This is the real photograph. And let's see, maybe I should stop it being a pointer. And So here, the only thing that was done is people colored left screws with green and right screws with red. But you can see that in rotating electric field, these molecules really come in motion. And if you wait, this is, by the way, in real time. And if you wait for a few minutes and you measure the concentration of left-handed and right molecules, then you see that they really sort of concentrate on opposite parts of this vessel, depending on chirality of the molecule. Okay, so this is, just amusing by itself, but it also is a mechanism in which you can separate molecules of different chirality and realize this chirally pure drugs that pharmaceutical industry desires. So now let's discuss the theory of chiral transport for objects with small size and small velocity. So here there was a very important observation which was made quite some time ago by Edward Purcell, who of course is famous for getting Nobel Prize in 1952 for his work on nuclear magnetic resonance. He was also advisor to the president for science and did many other great things. So he observed that motion at low Reynolds number is characterized by some special feature, which I am now going to discuss, which in fact, as we will see later, makes it quite similar to what happens in quantum transport when you take account of anomaly. So first of all, let us define what the Reynolds number is. So if you have an object of characteristic size A, it moves with velocity v in a fluid characterized by density rho and shear viscosity eta, then the Reynolds number is, loosely speaking, the ratio of inertial force to the viscous force. And this is the product of the size of an object, velocity with which it moves, density of the fluid, and divided by shear viscosity. So how do we make Reynolds number small? We look at small objects. That's why we concentrated on molecules. We make them move slowly. The density of the fluid should not be too large, and the fluid itself has to be characterized by a large viscosity. So if you introduce this quantity, which is the ratio of shear viscosity to the density of fluid, then it's just AV over this nu, and nu is 10 to minus 2 centimeters squared per second for water. So this gives you an idea of what are the characteristic sizes and velocities. So for instance, when you go for a swim in the ocean, then your Reynolds number is about 10,000. For little fish around you, it's about 100. And for these molecules and bacteria, this is 10 to minus 4. And so when you swim in the ocean and when bacteria swim in the ocean, the Reynolds number differs by 8 orders of magnitude, and fluid dynamics of this motion is drastically different. So what changes when Reynolds number becomes small? When we look at Navier-Stokes equation, it's famously nonlinear equation, and this is one of the big millennium problems, to characterize its solutions and so on. But if Reynolds number is small, then the right-hand side of Navier-Stokes equation can be neglected. And Navier-Stokes equation becomes the so-called Stokes equation, or equation of the creeping flow, as it is sometimes called. So this in this Stokes equation, as you can see, time does not matter, and in Purcell's words, the pattern of motion is the same, whether slow or fast, whether forward or backward in time. And Purcell formulated this in the form of so-called scallop theorem. And the point is that, the scallop is believed to move by, opening and closing its shell. So of course, if you buy, a scallop in a store or in the market, it's hard to believe that scallop can actually move. But as this movie shows, scallops actually do move on the ocean floor. But if scallops were tiny, and if their motion were described by Stokes equation, then they would not be able to move at all, because when they open the shell, they will move in one direction. When they close the shell, they will move in the other direction. And so their motion would be impossible. So, at some point, I gave a colloquium at the Institute of Marine Biology, and people who professionally work on the motion of scallops made a fun of me and Purcell and say that opening and closing shell is not at all how scallops move. But for the sake of the argument, let me assume that it is true. So the same argument of Purcell was also elegantly formulated by L. Shapiro and Frank Wilczek in terms of geometry of gauge field on the space of shapes. And so for scallops, this geometry is trivial. And they showed that in order to propagate this geometry of gauge field has to be topologically non-trivial. So before we go into this, let me just illustrate experimentally that time reversibility of Stokes flow is not just a theoretical argument, but you can really establish it in experiment. And of course, physics is an experimental science. And so we really want to see whether this is possible. So in order to establish reversibility of Stokes flow, let us use so-called Couette flow. So Couette was a French physicist born in Tours, France. And this Couette apparatus consists of two cylinders of different radii, and you put the fluid in between these two cylinders. You can rotate the interior cylinder, and this is what Couette proposed as an apparatus for measuring the shear viscosity. So now let me take this Couette flow, Couette apparatus. Let me consider some viscous fluid, such as glycerin. And let me put 3 drops of colored liquid inside this viscous fluid. So here in this demonstration from UNM, you see, experimentalists putting a drop of red dye, a drop of green dye, and a drop of blue dye. Okay, so then we have this three drops. And now in QET apparatus, you can rotate the interior cylinder. And so this is what these people are doing. One turn, two turns, three. Here is 4. And now is 5. And now you see that these 3 well separated drops, are completely mixed up. And, instead of these drops, you see a complete mess. So now you start rotating in the opposite direction, trying to perform the time reversal operation on this fluid. And you rotate exactly the same number of rotations in the opposite direction. You keep rotating. And once you come back to the initial, once you rotate back the same number of turns, you see that you reproduce the initial configuration of these drops. So this is, I think, is really quite amazing and is very different from our everyday experience. So imagine you take your, cup of coffee and you put in it a cube of sugar. You rotate a spoon, 5 times to the right. So the sugar gets dissolved, and then you rotate it, 5 times to the left, and you recreate the cube of sugar. Of course, this does not happen, and this is because we are in the Navier-Stokes regime when turbulent effects are important. But in the Stokes regime, when the fluid is very viscous, its motion is indeed time reversible. And this means that you do not produce entropy in the motion of this fluid. So we will see that very similar things happen in quantum dynamics due to time reversible nature of chiral anomaly. Okay, so now if you want to move, so if you want to give, let's say, this chiral molecule or a screw some longitudinal velocity, then of course this velocity breaks time invariance. And this means that if you want to ensure the chiral propulsion, you have to break time reversal. And of course, the screw itself breaks time reversal invariance. So in terms of formal theory, you can write the following equation, which expresses the force on a chiral object and a torque on a chiral object to its longitudinal velocity and angular velocity. And if the object is not chiral, then B and C of diagonal elements are equal to 0, which means that, let's say, if you just have a sphere and you push it with some force, it starts to move, but it does not start to rotate. Or you started to rotate, and it starts to, you put some torque on it, it starts to rotate, but it doesn't start to move. However, if you have a chiral object, an object which is characterized by some chiral imbalance, then this off-diagonal matrix elements B and C of this propulsion matrix are not equal to 0. And if, for example, you start to rotate an object like a chiral molecule, then it acquires also longitudinal velocity. Okay, so now let me evaluate this chiral propulsion using the language of quantum field theory, or field theory. This is actually classical field theory. So to do this, I will use the Green's function approach. So I start with the Stokes equation with the point force. I introduce the corresponding Green's function, which is known as a Stokeslet. And then if I'm interested in a solution for an arbitrary moving body and I have some velocity field, then I can evaluate this velocity field resulting from the application of the force F through this Green's function. And here, the integral goes over the surface of the moving body. So let's first consider a simple example of a sphere. And let me evaluate the fluid velocity at this point. So I'm going to use non-slip boundary conditions where the fluid does not slip along the surface of a body. And due to this non-slip boundary condition, the velocity here will be the velocity of the sphere. So this, by the way, is the work which I did with 2 first-year undergraduate students. So then the Green's function is singular, as you remember from the previous slide, but parity symmetry of the sphere, once you write down this integral and look at it, it's easy to see that parity symmetry of the sphere leads to cancellation of divergent terms, and then you find a very easily explicit answer. And here is what this answer is. And of course, this is a classic result by Stokes, which tells us that the velocity of this sphere under the influence of external force is equal to force over 6 pi shear viscosity times the radius of a sphere. Okay, so we have encountered no divergences here due to a cancellation due to parity, but the final result of our calculation contains the shear viscosity. And if you think of hydrodynamics as an effective low energy theory, which of course it is, then shear viscosity is really an ultraviolet cutoff of this low energy effective theory. Shear viscosity determines some shortest distance at which hydrodynamics makes sense. And so what we got here in the language of field theory, we got an expression with an explicit dependence on ultraviolet cutoff. So now let us move from a sphere to a propeller. So this time, in fact, there is no parity symmetry because this propeller is chiral, and divergences do not cancel. So you get this expression. It's highly singular, so you can introduce some cutoff here. And this is where you kind of get stuck because everything depends on this cutoff. And this is why my undergraduate students stopped following, the work which was also done in classical fluid dynamics. But then after some time, we decided to look at other components of the velocity along this tangential direction. And of course, we found the same divergence in this component as well. And then we realized that we can think in the language of quantum field theory, where divergences happen all the time. But if you express one observable through the other observable, then in these relations, the divergences do not appear, and you can still obtain meaningful results. And so this quantum field theoretical thinking is what allowed us to obtain a new result. And we showed that this relation between propulsion velocity and the angular velocity actually contains no divergences, and therefore does not depend on viscosity of the fluid. So you can just see it from explicit computation, and this chiral propulsion coefficient has no dependence on viscosity of the fluid in the Stokes regime. So there was some experimental and numerical evidence for this before our work, but I think it's probably the first explicit analytical demonstration that the chiral propulsion coefficient has no dependence on viscosity of the fluid. So no dependence on ultraviolet cutoff. And this, in fact, is the feature that makes this example of chiral propulsion in Stokes regime very similar to what happens in quantum transport due to the chiral anomaly. So then there is a next chapter to this story based on our very recent work with Stony Brook student Leonid Korneev and my friend Sasha Abanov. And the question that we addressed is, we know that chiral propulsion in Stokes regime is determined entirely by geometry. And so the meaningful question that one can ask is, what is the value of the pitch angle theta? So this is the definition of this pitch angle. It tells you, how big this tilt has to be. That is optimal for chiral propulsion. And so here we were able to derive a very simple dependence of this chiral propulsion coefficient on this pitch angle. It's cosine theta times sine of 2 theta. And of course, the theta that maximizes the value of chiral propulsion coefficient is arctan of 1 over square root of 2, which is 35 degrees. So then, once you know this 35 degrees, a natural question that arises is, what is the pitch angle of some chiral spiral bacteria that exist in nature? Well, there is a bunch of spiral bacteria in nature. Perhaps the most well-known is so-called spiral plasma nulliferum. So spiral, of course, because it has a spiral helical form. And, there are many papers. So this is a real photograph where you can see, these spirals. And, I tried to kind of read off the pitch angle from all of these images. but then I read this paper more carefully, and I found the following sentence. So the paper says the helical pitch angle observed for the helical spiroplasma melliferum is 35 degrees. So this is, you see, this is the same 35 degrees that you get out of this analytical computation. So somehow the evolution allowed this bacteria to optimize the pitch angle. Okay, so of course, there are many interesting stories behind chirality as well, which include light, and this will also be a big part of our story. And in particular, chirality is the mechanism which your eye uses, because the light induces transitions between right-handed and left-handed molecules in your eye, and the proteins in our bodies detect this chiroptical switches, and this is the reason you now see my slides. So it's really this transitions between two different chiral forms. And there is a new emerging field of chiral photopharmacology, which actually utilizes these transitions for medical purposes. So this can be done using circularly polarized light if you want to maximize transitions to one particular chiral form of the molecule. So last month we organized a Nobel Symposium on chiral matter in Stockholm, and Ben Feringer, who got a Nobel Prize for his work, demonstrated that these transitions can be utilized in particular for creating molecular machines. So he showed an image of a real car, with wheels built out of chiral molecules. And once you shine circularly polarized light on it, then the car comes in motion, and this all happens at nanoscale. Okay, so now since we started talking about light, a natural question is what is the role of chirality in Maxwell electromagnetism? And if you look at Maxwell equations, then of course you immediately observe that there is no breaking of chirality in Maxwell theory. It is left-right symmetric, and you can have both left-handed and right-handed circularly polarized states of light. And what is going to be very important for us, and which will be discussed tomorrow, is how do we classify the topology of light or gauge fields in general, and what are the topological invariants that can be used for this purpose. Okay, so it's 10:50 a.m., so I would like to stop here and leave time for questions and discussions. So thank you very much for your attention.
Thank you, Professor Kharzeev.